What if we told you a blurry picture, like one of those out-of-focus snapshots, could unlock the secrets of the invisible universe? Pretty wild, right? But that's exactly what's happening right now with this new space telescope called Euclid.
Yeah, it's really amazing.
So Euclid launched back in 2023, and its whole mission, its reason for being up there, is to map the universe, right? To
Right.
help us understand dark matter and dark energy.
Exactly. The stuff that makes up, well, most of the universe, but we can't even see it. It's a huge
It's like
challenge.
trying to figure out how a clock works just by looking at the hands, right?
Perfect analogy. We're missing the gears, the springs, the whole inner workings.
Okay, but here's the thing. Back in September 2023, Euclid was still in its, testing phase,
Right.
getting all its instruments calibrated, fine-tuned.
Crucial step. Got to make sure the data's reliable, Can't have wonky instruments up there.
Exactly. So they snapped this picture of a galaxy called NGC 6505, but it's blurry, out of
Yeah.
focus.
A bit of a cosmic blooper.
Not exactly what you want for a test image. But here's the twist: hidden in that blurry image was something truly extraordinary.
Something totally unexpected. A faint ring of light.
And that something turned out to be a near-perfect Einstein ring, predicted by Einstein's theory, but rarely seen this clearly.
It's like the universe decided to draw a perfect circle just to mess with us.
All right, so imagine this distant galaxy, billions of light years away, its light's traveling towards us. But on its way, it passes by this massive object. In this case, the galaxy NGC 6505, which is closer to us but still, crazy far, like 590 million light years away. And the gravity from that galaxy is so strong, it actually warps space-time.
Imagine a bowling ball on a trampoline. Yeah. It creates a dip in the fabric, right?
Right.
Now, if you roll a marble past it, its path curves around the bowling ball. Light does the same thing when it encounters a massive object.
Except instead of a trampoline, it's bending space-time.
Exactly.
Okay, so that light, instead of traveling straight, it gets bent around that galaxy, creating this ring of light. We see it as an Einstein ring.
Nature's magnifying glass.
Okay, so we have this ring in this blurry image, but why is this such a big deal? I mean, besides the whole Einstein was right thing, which is always cool.
Yeah, well, it's like this. This Einstein ring gives us a unique way to study dark matter in that galaxy. And dark matter, it doesn't interact with light. We can't see it directly.
Right, it's invisible.
It's like trying to study a ghost. You know it's there because things move around, but you can't actually see it.
So we know it's there because of its gravity.
Yeah, exactly. And gravitational lensing, like this Einstein ring, is one of the best ways we have to map its presence.
So how does that work?
Think about it. The shape of that ring is determined by the total mass of the galaxy. That includes the stuff we see, the stars and gas, but also all that dark matter we can't see.
So by studying the ring, we can figure out how much of that mass must be dark matter.
Exactly. Like how it deviates from a perfect circle, how bright it is. All these things tell us about how the dark matter is distributed within the galaxy, like using a shadow to figure out the shape of the object, right?
Wow. Okay, so we can learn about dark matter. But there's something else too, right? That galaxy, the one whose light is making the ring, is estimated to be 4.42 billion light years away,
Mind-boggling distances.
which means we're seeing it as it was 4.42 billion years ago.
Back when the universe was a baby, like a time machine almost.
Incredible.
Yeah.
But what does this say about the telescope itself? I mean, if it can make this discovery before it's fully operational,
It's exceeding expectations.
it means it's really powerful, really sensitive, like it tripped over a gold mine while just learning to walk.
A very good analogy. But let's delve into how Euclid actually made this discovery, the nitty-gritty of its instruments. We need to talk about VIS.
VIS. Okay, break it down for me.
So the VIS instrument, it's essentially a really high-tech camera taking pictures in visible light. It's Euclid's eye, so to speak.
I see. So that's what captured that first blurry image.
Exactly. And even though it was blurry, it was still sensitive enough to pick up that faint ring of light.
So VIS is important, but Euclid's got another trick up its sleeve, right?
Oh, yeah. It has the NISP instrument. Stands for Near-Infrared Spectrometer and Photometer.
Okay, that's a mouthful. What does NISP do?
It's all about measuring redshifts, which is basically how we determine the distance to those faraway galaxies. It does this by looking at light in the near-infrared part of the spectrum.
Redshift. Right, so the farther away something is, the more its light is stretched toward the red end of the spectrum. It's like a cosmic Doppler effect.
Precisely. And NISP measures that stretching, that redshift, so we can map things out in 3 dimensions.
Wow, that's pretty cool.
Yeah, it's more than just distance, though. NISP also helps us figure out what those galaxies are made of by analyzing their light in different infrared bands.
So VIS and NISP work together to give us a more complete picture, like a cosmic dream team.
I like that. That teamwork was crucial for this Einstein ring discovery. VIS caught the shape, and NISP helped pin down the distances. But there's another factor here, Euclid's wide field view.
Okay, how does that play into this?
Well, think about it. Einstein rings are pretty rare, right? You need a very specific alignment between us, the lensing galaxy, and that distant source. It's like trying to find a needle in a haystack.
And Euclid's wide field view is like having a bigger haystack to search through.
Exactly. It allows Euclid to scan large portions of the sky, increasing the odds of finding these rare alignments.
It's all about increasing the chances of a cosmic encounter. So we have these incredible instruments, VIS and NISP, working together to capture those images, measure those redshifts, all while scanning this vast area of the sky.
It's truly remarkable what we're able to do with modern technology, and the teams behind these instruments are just brilliant.
It's like they built a time machine and a dark matter detector all in one.
I wouldn't say that's too far off.
It's amazing, but we've talked about dark matter, and now I'm thinking about another mysterious force out there, dark energy. This stuff that's making the universe expand faster and faster. How did this all fit into that?
Ugh, dark energy. One of the biggest puzzles in cosmology. And yes, this Einstein ring discovery can tell us something about it, though indirectly. You see, how many Einstein rings we find at different distances, what we call their redshift distribution, is linked to how the universe has expanded over time.
Because the farther away the ring, the longer the light has been traveling, and therefore...
And therefore, the more the universe has expanded during that time, and the rate of that expansion is all tied up with dark energy.
So by studying lots of these rings across different distances, we can get clues about dark energy.
Exactly. It's like using these cosmic lenses to measure the stretching of the very fabric of space-time.
Okay, this is where my brain starts to melt a little. But it's exciting to think that we can use these distorted rings of light to unravel some of the universe's biggest mysteries.
It is pretty mind-blowing. And it just shows the universe is full of surprises, and sometimes it reveals its secrets in the most unexpected ways. Welcome back to our deep dive into these fascinating Einstein rings. Before the break, we were talking about how Euclid found this ring by accident, and what that tells us about the telescope's capabilities. Now let's get into how scientists actually squeeze so much information out of these things. All right. I'm ready for a crash course in cosmic detective work. What are the tools of the trade?
Well, imagine you're a detective at a crime scene. You've got footprints, fingerprints, maybe even some DNA.
Right, those are the clues.
Exactly. And each clue tells you something about what happened, right? Analyzing an Einstein ring is kind of like that.
Okay, so instead of dusting for fingerprints, we're analyzing warp to light.
Exactly. And one of the key tools is something called image deconvolution. Basically, a way to sharpen those blurry pictures we get from telescopes, like Photoshop for space, if you will.
Ah, so they're cleaning up the image to get a better look at the ring. Right. Even with powerful telescopes like Euclid, you get some blurring from the atmosphere, the telescope itself, all sorts of things. Image deconvolution helps remove those blurring effects, revealing the true sharpness and detail of the Einstein ring.
So we sharpen the image. What's next?
Next comes lens modeling. Remember, the shape of that ring is determined by how the mass is spread out in that lensing galaxy. Lens modeling uses, well, pretty complex math to reconstruct that mass distribution, including the dark matter.
It's like trying to figure out the shape of a mountain by looking at its shadow, right?
Another great analogy, and astronomers use different models, each based on some assumptions about how dark matter behaves. They compare these models to the actual shape of the Einstein ring, tweaking things until they get a good match.
It sounds like a giant cosmic jigsaw puzzle.
It really is, and it takes a ton of computing power. These models can get super complex, especially when the galaxies aren't perfectly round or when there's more than one galaxy involved.
Wow. You know, whenever we talk about crunching huge amounts of data, I can't help but think about artificial intelligence. Is AI playing a role in all of this?
Absolutely. Astronomers are now using machine learning to analyze Einstein rings. For example, they're teaching algorithms to automatically spot those rings in the mountains of data from telescopes like Euclid.
So instead of having scientists pore over millions of images, we can have computers do the initial screening.
Exactly. It's a game changer. It really speeds things up. And machine learning can even be used to refine those complex lens models we talked about so we get better, faster results.
Sounds like machine learning is revolutionizing astronomy, just like it is in so many other fields.
Oh, yeah, it really is. It's like we're suddenly able to do things we could only dream of a few years ago.
This is all fascinating, but I have to admit, my brain is starting to fry a little with all these technical details. Can you give me a concrete example of how this all comes together to tell us something meaningful about the universe?
Sure. Let's go back to that Einstein ring around NGC 6505. By applying image deconvolution, scientists were able to sharpen that blurry image, seeing subtle details in its shape and how bright it is at different points.
They get a much clearer fingerprint, so to speak.
Exactly. And then they used lens modeling to reconstruct the mass distribution of NGC 6505, including both the visible matter and the dark matter. What they found was that the dark matter halo of this galaxy extends far beyond the visible stars and gas, and that confirmed predictions from cosmological simulations.
So this blurry picture, this accidental discovery, gave us solid evidence about the invisible structure of a galaxy millions of light years away.
It did. And it's a glimpse of what Euclid will be able to do on a much larger scale, mapping thousands of Einstein rings across the universe, each ring giving us a little snapshot of how dark matter is spread out.
So we talked about how these techniques help us study dark matter. But what about dark energy? How does looking at Einstein rings tell us about that mysterious force that's making the universe expand faster and faster?
Well, remember we were talking about how many Einstein rings we find at different distances, their redshift distribution?
Right, because the farther away the galaxy, the longer the light has been traveling.
And the more time the universe has had to expand, right?
Yes. And that expansion rate is all tied up with dark energy.
Exactly. So by studying a large sample of Einstein rings at different redshifts, Euclid can help us understand dark energy better. We can figure out things like its equation of state, which tells us how its density changes as the universe expands.
So it's like using these cosmic magnifying glasses to study the very fabric of space-time and how it's being stretched by dark energy.
A very good way to put it. It's an amazing feat, really. By studying these tiny distortions of light from billions of light years away, we can untangle some of the most fundamental forces that govern the entire universe.
Mind-blowing. But I'm curious, are there any limitations to these techniques? It all sounds so incredibly precise and complex.
Of course, no method is perfect. One of the challenges in studying Einstein rings is dealing with what we call foreground contamination. Think about it, we're looking at light that's traveled billions of light years.
Right, an incredibly long journey.
And along the way, that light might pass through other galaxies, clusters of galaxies, even clouds of gas and dust.
So there could be other stuff besides the main lensing galaxy affecting the light.
Exactly. And that can make the analysis a lot trickier. It's like trying to read a fingerprint when it's smudged and overlapped with other prints.
So how do astronomers deal with that? How do they make sure they're focusing on the right signals?
They have to carefully model and subtract out the light from those foreground objects. They use observations in multiple wavelengths of light to help disentangle everything.
So they're like cosmic archaeologists,
Mm.
carefully brushing away the dust and debris to reveal the hidden treasure.
Great analogy. It's a painstaking process, but crucial for getting accurate results. And then there's another challenge, which is that our understanding of dark matter and dark energy is still, well, a work in progress.
Right. We're learning as we go.
Exactly. So the models we use to analyze those Einstein rings might not be perfect yet. It's like trying to build a house with a blueprint that keeps changing.
But as we learn more, those models will get better, and we'll be able to squeeze even more information out of those cosmic lenses.
Exactly. It's a really dynamic and exciting field, always pushing the boundaries.
So where do we go from here? What's the next chapter in this cosmic detective story?
Well, Euclid is a big piece of the puzzle, but it's not the whole story. There are other missions on the horizon, even more powerful telescopes and observatories, and each new generation of instruments helps us see farther, deeper into the past, uncovering more secrets.
Sounds like we're just getting started.
We are. It's a golden age for cosmology, really. And with new discoveries happening all the time, who knows what we'll find next?
It's pretty humbling, but
Yeah.
also incredibly inspiring. But, we've talked a lot about this amazing technology and complex science, but I'm wondering, is there any role for regular people in all of this? Can someone without a scientific background contribute to the study of Einstein rings?
That's a great question, and the answer is absolutely yes. Citizen scientists are already making huge contributions to astronomy, especially in projects that involve looking at tons of data.
Because even with machine learning, some things are still easier for human eyes to pick out, right?
Exactly. And there are actually citizen science projects dedicated to finding gravitational lenses, including Einstein rings. One example is space warps, where volunteers look at images from telescopes and mark anything that looks like a potential lens.
Wow, so you don't need a PhD to help understand the universe. Anyone with a computer can potentially make a real contribution.
It's true. It's a testament to the power of technology and to that basic human drive to explore and understand the world around us.
We've covered so much ground in this episode. It's clear that the study of Einstein rings is a fast-moving field with huge implications.
It is, and it's changing how we see the universe. These cosmic lenses are giving us incredible insights into dark matter, dark energy, and even the fabric of space-time itself.
It's a lot to wrap your head around, but it's also incredibly exciting. It feels like we're on the verge of some major breakthroughs.
We are. And with missions like Euclid constantly gathering data, I have no doubt the next few years will bring even more incredible discoveries.
Welcome back to the Deep Dive. We've been on this incredible journey, haven't we? Talking about how a blurry picture from the Euclid telescope, just a test image, actually revealed a near-perfect Einstein ring. And what's amazing is how this has cracked open a window into the dark side of the universe.
It's pretty poetic when you think about it. You have this light traveling for billions of years, then it gets bent by the gravity of a massive galaxy, and we end up seeing this delicate ring from Earth.
It really makes you realize how huge the universe is, and also how everything's connected in these mind-boggling ways.
It really does.
And we're only just beginning to grasp what all these cosmic signals actually mean.
Yeah. With every Einstein ring we discover, we're deciphering a little bit more of that invisible scaffolding of the universe, all that dark matter and dark energy that shapes how the universe evolves.
So if this one accidental image has already told us so much, they expect Euclid to find thousands more of these rings, right?
Yeah, thousands, maybe even tens of thousands, a whole treasure trove of data.
It's almost overwhelming to think about.
It is. And by analyzing all that data, we'll be able to map out dark matter across a vast volume of the universe in 3D, which will really change how we understand how galaxies form and evolve.
Okay, so we'll be able to map dark matter better than ever before. But will we finally know what this mysterious stuff actually is?
That's the big question, isn't it? But by studying all these Einstein rings, their shapes, sizes, brightness, we can test different theories about what dark matter is made of. Is it these weakly interacting massive particles or something even weirder? Euclid might just give us the answer.
It's exciting, but I have to admit, when I really think about how vast the universe is and how much we don't know, it kind of makes me feel insignificant.
Yeah.
Like our little planet is just a speck of dust.
I get that. It's a natural reaction when you think about the scale of things. But I think there's another way to look at it. We're these tiny beings on a tiny planet, and yet we can actually grasp these cosmic concepts. I think that's pretty amazing in itself.
You're right. We have this drive to explore, to understand everything around us, no matter how huge or complicated it seems.
And these Einstein rings are a perfect example of that. It's pure curiosity, human ingenuity, and technology all coming together. We're using these tiny distortions of light to understand the deepest mysteries of the universe. I find that pretty awe-inspiring.
Me too. The universe is full of surprises, and we're always coming up with new ways to explore it. So what's next? What other frontiers are out there for us to discover?
Well, Euclid is just the start. There are other missions planned, even more ambitious telescopes and observatories in the works, and each new generation of instruments allows us to see further, deeper into the past, revealing more and more of the universe's secrets.
It sounds like we have a lot to look forward to.
We do. It's a golden age of discovery, and who knows what amazing things we'll uncover next.
Well, you've definitely given our listeners a lot to ponder. I know I'm feeling incredibly inspired. Any final thoughts before we wrap up?
Just this. Keep looking up, keep that curiosity alive, and never stop exploring. The universe is waiting for us.
I love that. Well, that's all the time we have for this deep dive into the world of Einstein rings. Thanks for joining us, and until next time, keep exploring the cosmos.